Greetings. We're at a park very near my house, and it's actually a special water body that you see behind me. There was an old landfill here. Like many old landfills, it was likely improperly lined, and many old landfills leach a variety of pollutants into the ground and surface water. Those pollutants can range in their identity from things like sodium, potassium, kinds of ions in there, to things like vinyl chloride, heavy metals, cadmium, and just broadly, water pollutants can be of a variety of natures, organic, inorganic. You've probably all heard about things like oils and greases that contaminate water. So I want to start by thinking about the salts, and in fact, sometimes a polluted water body can become hypersaline, and how we might go about detecting that hypersalinity or just salinity in general. Remember that we just learned that those ions in solutions that are salts that get pulled apart by water, there's a salvation sphere that forms around those ions, and of course they conduct a current. Now, thinking deeply about that salvation sphere has been on my mind lately. And in fact, if you have, say, a sodium cation, you'll likely get a shell around that you may have 6 coordinated waters around that. So what I want to see today is how we could take simple tools out into the field and actually detect things like conductivity. Now, one of the tools that I brought today is not one that you would probably take out to the field, because we've actually carried in a 200-watt power supply because we're really close to the road and we can actually show you that. But on the other hand, if you're out in the field, you'd want to be carrying something more like this simple TDS meter, and we'll look at that in a minute. So we know if I've got a control here, this is a 1 molar sodium chloride solution. We recognize that this is going to carry a current that we can take a conductivity meter and measure and see, or visibly see, that that current flowing from one electrode to the other. So this is actually a light bulb plugged in that has 2 open electrodes. So in theory, if we have ions in solution, when we put this in there, it will close the current and we will be able to see the light bulb light. So there's your light from the 1 molar sodium chloride. You're envisioning those salvated or hydrated ions, allowing that light bulb to light up.
Let's look a little bit closer at what's going on in the solution. We know that in water, the sodium chloride dissociates into its solvated component ions. Of course, the sodium cation migrates to the negative electrode, or the cathode, and the chloride anion is going to migrate to the anode, the positively charged electron. It is, of course, at that location going to be oxidized, and at the cathode, the sodium cation is reduced, allowing for the current to be conducted. But notice that this drawing is rather simplistic, because we know that the ions are actually surrounded by a solvation or hydration sphere. Remember looking previously at the drawing of the sodium cation with a hydration shell that was comprised of 6 water molecules. The sodium cation was at that octahedral hole, interacting via ion dipole interactions with the water molecules, recognizing that the sodium cation will form ion dipole interactions with the oxygen of the partially negatively charged oxygen will form ion dipole interactions with that sodium cation. Now, with the chloride anion, there's also going to be that hydration shell, but of course the ion dipole interactions will be between the partially positively charged hydrogen atom and the negatively charged chloride ions. So that hydration sphere, while also commonly containing 6 water molecules, the water molecules are oriented differently within the shell of the chloride anion. It's also interesting to note that, in fact, generally we don't just see one layer of interacting water molecules or a single shell. We generally see a double shell, or in some cases, we see very complex in sodium ion clathrates, for example, in which 20 water molecules may cage the sodium cation, and it may in fact rattle around in that clathrate cage. So when we show the negative and positive naked ions in order to show conductivity, we're really simplifying. And in fact, we know there's a lot more complexity about the way in which the salvation cages are forming around the ions.
Well, one thing that you might be saying to yourself there is, heck yeah, sodium chloride, that's an electrolyte. I know that well. If you get cramping, maybe you drink a little extra, eat a little extra sodium chloride. Oh yeah, and then you're thinking, how about Gatorade? So I've actually made up a strong solution of Gatorade. This is probably a little stronger than you would typically want to drink for replenishing your electrolytes after a workout. But I wanted to see if we could see this electrolyte carrying a current. So bingo, not as bright as the 1 molar sodium chloride, but certainly it shows us conductivity is happening, that yes, there are ions that are carrying the current in that solution. So now the other thing that I have done is I have collected water from the pond behind us. And we might want to say, hey, do we think this is contaminated with electrolytes, with varying pollutant ions or naturally occurring ions? And will we see that the conductivity meter shows us that? So I'm going to put that in there. And there's a little bit. So we are showing that this is conducting a current. So that's an interesting observation. As I said, though, you probably wouldn't carry this out into the field to measure ions. And instead, you might take something like this simple TDS meter. This TDS meter actually measures total dissolved solids. Total dissolved solids doesn't necessarily indicate just our electrolytes. So when you take a measure with this meter, you have to convert it to millisiemens from parts per million. But we can get a parts per million read here to see where we are with our water from the pond, and recognize we're at 102, 103 parts per million. Now, the interesting thing is that water is considered okay to use for growing food or in agriculture if it's under 75 ppm. So this particular water is too polluted to be used for growing food. It's an interesting note that this simple measurement can be one that helps us to monitor water quality. Another common contaminant in water is, of course, oil and grease, and we've all heard about oil spills in particularly marine water. So what I've done here is I've gotten a certain amount of water out of the lake, and I've placed it into a very shallow receiving vessel so that we can look at the effects of putting some droplets of oil into water. We know oil and water don't mix, right? But have you ever thought really deeply about both the entropic and enthalpic consideration of why that is? So what I'm going to do is I have mineral oil here, just happens to be what I have. You can do this at home with vegetable oil or olive oil. And so we're going to just drip some drops of oil into the water. These droplets of oil, you might make a hypothesis that either the oil is wanting to be together or the water is pushing the oil together. And in fact, the latter is really more the hypothesis that we would affirm. And there's both an entropy and enthalpy going on here. Now, on the one hand, enthalpy is actually going to be to disfavor the pushing together of the oil droplets because of van der Waals forces that it engages with the oil and likes to interact from an enthalpic point of view. But despite the thermodynamics, the entropy of water molecules is very, very much decreased when the water molecules have to become ordered around the oil. That's very entropically unfavorable. So by pushing the oil together, they increase their capability of being disordered. And so with respect to entropy, it's favorable for those oil droplets to coalesce, decreasing the surface area of the oil exposed to the water. Now, it's interesting to note, and some of you might have been noticing that while we were observing, that the oil, yes, it did coalesce, but it also looked like the droplet got bigger and bigger and bigger on the surface of the water. And that can be a confusing observation. But the way that I like to think about it is that if you're out swimming in a lake and you want to maximize your suntan surface, you are going to back float instead of treading water with most of you down. And if you think about that, you're actually decreasing the surface area that's exposed to the water, increasing the surface area that's exposed to the air. So that's how I like to explain what's going on with that. So now you might be thinking back to the Gulf oil spill, and you might be thinking about a company that got a really big boon in the Gulf oil spill, and that was Dawn dish soap. And that you'll notice, in fact, they have a bird on the front of their advertising marketing campaign because they use this to clean birds who had been badly affected by the spilled oil. You might have also heard all the advertisements, not just by Dawn, but any kind of detergent where they say, we cut grease best, or we trap grease, we trap oil in grease. And that's referring to what's going on here. So if we want to see what Dawn dish soap does to a droplet of oil, we can layer this on the surface of the, and you're going to have to look close here. I'm going to layer it on the surface right over here, and we're going to see if we can see an impact. So boom, boom, cuts grease. So what was happening just then is that the detergent molecules were hit the water and they put their hydrophilic heads down onto the water surface. They stuck their hydrophobic tails up. They're like, I don't want to have anything to do with the water. And it formed a monolayer of heads all expanding across the water. And that pushed the oil to the side. It would cut grease, right? Really quick like that. But now, say we were trying to wash things up, we would mix that around and we would start to see what would happen here is that we would start to see the formation of what are called micelles, because now the detergent, its hydrophobic tails point inside in what looks like a single layer, almost vesicle that puts the grease on the inside with all the hydrophobic tails of the detergent, and then the hydrophobic grease, the hydrocarbons are trapped. So literally, detergent is trapping the oil inside of the micelles. So this was one attempt, right, to clean up polluted water.